All right. Welcome to the afternoon session. I'm Philip Paeps. I wear many hats. One of my hats is I am a FreeBSD developer and itinerant FreeBSD presenter. And this is a, well, notionally this is a one-day workshop on ZFS. I've taught in many parts of the world now. I also have a 3-day workshop on ZFS, which I was originally going to use for this talk. But then I found that I'd accidentally once taught a 1-day workshop. So that's slightly less embarrassing. The good news is that these slides have all of the demo bits and bobs in them. And I think these slides have been uploaded to the conference. If they have not, I will upload them to the conference webpage. And if the conference webpage does not allow me to upload things, this presentation is also on papers.freebsd.org, or it will be in due course. So I have 45 minutes, I think, and I'm going to cover about a day's worth of material. So we'll see how far we get. And the trick to this is, of course, to speak faster and faster and faster and faster and faster until you're out of breath. But I'll try to contain myself. So a brief history of ZFS. Has anyone here not ever heard of ZFS? You might know it as ZFS if you live on the other side of the ocean. Okay, so everyone has heard of ZFS, fantastic. A bit of the history of the file system. It was originally developed at Sun in the early 2000s, about 2001, and was developed for Solaris or Sonos, and it worked really well there. And in 2005, they decided, let's release it as open source. Hooray, open source is great. So they released it as open source, and about 3 years later, it landed in FreeBSD 7, and it was reasonably mature. As of 2019, ZFS still doesn't work reliably on Linux, though I hear that this is improving, which is great. Let me say that I'm actually really happy that we're getting this open ZFS effort going, because competition is good in any market, and having more eyeballs is always good. But FreeBSD has a very mature implementation of ZFS, and it's mature in the sense that it's been running on FreeBSD for over 10 years, well, nearly 12 years now. So people have been using it as their root file system on FreeBSD for the past 12 years. It does not eat your data. It does not kernel your files. It's rock solid on FreeBSD. It is also, as you'll see in my demos, it is really, really easy to use on FreeBSD just because it's so well integrated with the operating system. But enough about the history. Let's get into a nutshell of what ZFS does. You've probably heard this several times before, but ZFS provides 4 key things. It provides end-to-end data integrity, which means that it detects silent data corruption at any point in the data pipeline. So from you creating your file to it hitting your block device, and then your block device silently gobbling up your blocks as it runs. ZFS provides pooled storage, so it's a 128-bit file system. That's not very exciting by itself. It just means that the pointers are very long. But as a side effect of this, it eliminates the antique or baroque notion of volumes. When traditional Unix-style file systems, you have to think ahead, you have to predict the future, right? How many files am I going to have 10 years from now, and how much space do I need for them? And you need to predict the future, and you always get it wrong. So volume managers are the bane of anyone's existence who's used computers in the 90s and early 2000s. ZFS just does away with all that. It's both a file system and a volume manager in one, and the file system just grows as you add more storage. Instead of having to, you buy a new disk, you repartition, you create volumes, and then you create your file systems, you take away the middle steps, you just add more disks, and the file system copes with it for you. ZFS also has a transactional design, which means that your data is always going to be consistent. I'm a device driver hacker. My joy in life is cranking out device drivers. My kernel panics all the time. I write bugs, my kernel panics, and my file system stays consistent. ZFS, I can unplug the power at any point in time, and my data is consistent. With other Unix-like file systems, if you unplug the power at an inopportune moment, you lose data, and you're spending, half of your life running FSCK. This is a thing of the past in ZFS. As a side effect of this reliability, you also get huge performance wins, which, some people think performance is the main thing. I like reliability a bit more. But the transactional design of ZFS means your data are always consistent, and you get huge performance wins. More on that later. And it's very simple administration. I do not wish to be a systems administrator on any of my machines. I'm a kernel hacker. All I care about is, can I get to my files? ZFS is very simple administration. You need exactly 2 commands to manage your entire storage configuration. You need zpool to manage the pools and ZFS to manage your file systems. More on all of that later. So let's talk a little bit about end-to-end integrity. Any of these things can fail. A hard disk's joy in life is eating your data. When you write data to a hard disk, what you are doing is you are feeding the disk. It's a little monster. It just eats your data. Its joy in life is to corrupt your blocks. That's what it's for. Disks have firmware. Firmware has bugs. We know some software. We know some firmware engineers. There might be one of them in the room. Bugs are everywhere. Disk firmware is hideously untrustworthy. Disks are plugged into controllers, SATA controllers, SAS controllers, SCSI controllers. All of this stuff runs firmware. Firmware is written by people like me. It has bugs. That's what we do. The disk controller is going to corrupt your data. The cables rot. Regardless of what they're made of, they rot. After a while, the cable just starts to corrupt your data. Talked about firmware. Device drivers, the SATA driver, the ATA driver, all of those things, they just corrupt things. Finally, at some point in time, your data is going to live in memory. The memory is also going to get corrupt. So, if you've got ECC memory, it's going to corrupt a little bit slower. But if you have non-ECC memory, it's just, it's going to corrupt. So, what do we do about this? Traditionally, we have disk block checksums, where we store a checksum of the block together with the data block. So, if you have a piece of data, we calculate the checksum of this data, and we store it together with the data block. This is all well and good. Unfortunately, if the block is self-consistent, so if the corruption is there before you calculate the checksum will be quite correct, right? It's great, it's wonderful. You have authenticated corrupt data. This is fantastic. So these block checksums, they protect you against bit rot. So if your disk starts lying to you or your cable starts rotting, the disk block checksums will detect that category of error, but there's more errors than that. So bit rot is just one class of things breaking. You can have phantom writes, where the disk suddenly decides out of the blue, today is a good day to write a bit, and it goes and writes a bit somewhere where no bit is expected. Or misdirected reads and writes, where you write to your bit of spinning Rust, you write some blocks, and suddenly you miss, for whatever reason, physics, the cat's kicking your computer. Something happens, so a read or a write is misdirected and a bit falls over. These things happen. A disk block checksum is never going to catch that. DMA parity errors, driver bugs, accidental overwrites, all sorts of things that can go wrong, and your disk block checksum is simply not going to detect that category of failures. So the only thing the disk block checksum does is it will validate media, so it'll protect you against bit rot, essentially. ZFS is a little bit smarter than disk checksum, than block checksums. Instead of putting the checksum with the data block, it puts it in the parent block and it builds a tree. If anyone's ever used Git, anyone used Git? Everyone's used Git. This tree structure should be familiar to you. It is exactly the same tree structure that Git uses. It's a self-validating Merkle tree, a hash of hashes, or a tree of hashes that validates. So the entire storage pool is a self-validating Merkle tree, it's a very efficient structure for validating tree-structured data. What the ZFS authentication does is it validates your entire I/O path. So in addition to the bit rot, the chains block checksums can also detect phantom writes, misdirected read and writes, parity errors, and even device driver bugs, which, those of us writing device drivers don't like this, but, hey, we have to grow up someday. So ZFS will keep will keep an eye on your data or the integrity of your data in the background. All of this happens without you having to do anything. Software just does this for you. Keep an eye on the time. That was integrity. Let's move on to storage architecture. So I mentioned pooled storage. In the past, back in the mists of time, we used to have a file system layout or an architecture that looked a little bit like this. You have your disks at the bottom, you have a volume on top of that, and you have a file system on top of that. If you've got a file system on a 1 gigabyte disk, you've got your disk and your file system lives on top of that. That's easy. If you want to go into a little bit more exciting kinds of storage, you would get a stripe or a concat where one disk will have the lower 1 gigabyte of data, the other disk has the upper gigabyte of data. You stick a volume on top of that, and then your file system on top of that. If you want to add a disk, you'll need to add your disk, you'll need to recreate your volume, and then recreate your file system on top of that. If you've got a stripe where you put the even blocks on one disk and the odd blocks on the other disk, again, there's a volume on top of that and a file system on top of that. And finally, you could have a mirror where the left hand of the mirror and the right side of the mirror, and then a mirrored volume on there. Writes go to both of them, but again, your file system is on top of that. The problem with that is that every file system has limited I/O bandwidth. You can only have the bandwidth of one disk at a time, and you have to manually resize your file system. So every time you add disks, you need to go and manually resize them. This is terribly boring, and your storage gets fragmented over time. So as you keep adding more and more disks, your data starts living in more and more places. It becomes more and more fragmented. So accessing certain files might take longer for reasons that become more and more difficult to explain. ZFS has something called pooled storage. So you just add a disk, 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 and you have the notion of a pool on top of all those disks. So if you have 20 disks, you have a storage pool. You still have one storage pool. You've created it once, and it grows automatically. You keep adding disks, the pool keeps growing. You don't even need to think about it. And your file systems, you create them on top of the pool. Is that clear as mud? Yes. ZFS has copy-on-write transactions. I'm just whizzing through these things. Copy-on-write transactions basically means that you cannot ever have your file system in an inconsistent state. So your file system is consistent. When you create a file or copy a file or do anything to your file system, you copy on write the blocks, then you copy on write the indirect blocks, and finally, when all of the other bits of housekeeping have been done, at that point you rewrite your, what ZFS calls the Uber block, in one atomic operation. So it's at no point in any of these four things ZFS does is your file system inconsistent. So if you're a device driver writer, or you're otherwise fiddling with your kernel underneath, or you are the sort of person who likes to unplug your computer while it's doing things, your file system is going to survive this. You might lose the data you're writing, the newly written data, but your file system is not going to be corrupt. Yeah, I heard a scream of terror. No, no. So if you unplug your computer before the Uber block's written, you've lost all the bits in the middle, but your file system is not going to be inconsistent when you boot your machine again. It's don't unplug your computer. But you're not going to lose your file system to unexpected events because of this copy-on-write transaction mechanism. Finally, ZFS has simple administration. So you've got two commands. All of these things, gpart, fdisk, fusk, newfs, mount, etc, fstab, you can throw them away. Isn't it nice? I can't remember the last time I ran FSCK. It used to be about a third of the CPU time on my computer went into FSCK. This is all gone. So you have two commands in ZFS. You've got zpool, which you use to add and replace disks, and also to resize pools. On FreeBSD, I think we resize them automatically now. I've not checked. I might be lying. But if it doesn't do it automatically, you just set a flag, and you resize automatically. And then finally, you have the ZFS commands, which you use to do all the things with the file system, like set quotas and reservation, enable compression and deduplication. More on that in a bit, if we have time. Snapshots and clones, and all of the the little grubby Unixy flags on file systems, which we all know and love, like access time and read-only, and all that. So. Right, with that said, I am sick of slides. I don't like slides. Let's talk about storage pools. In the real world, when I'm teaching this, I would have you all pull up your laptops with VMware and FreeBSD. But we don't have that luxury here. Let me find a terminal. how do I get my, my terminal is on the other side of the screen. Hooray. Is everyone young enough to read this? Tell me when to stop. Like there.
There's people watching online as well. So
hello, the internet. All right, so I have a fresh FreeBSD machine. I installed FreeBSD during the previous talk. I'm very well organized. If you run FreeBSD, you get ZFS by default. In fact, you will find that FreeBSD will install ZFS as your, bigger. All right, Ben says bigger, so bigger. There we go. Screen real estate, good for us. FreeBSD will install ZFS. The installer will use ZFS as its root file system. This is really awesome stuff because one of the things ZFS does really well, which I hope to have time for, is snapshots. Normally, FreeBSD upgrades do not break your machines because we believe in the principle of least astonishment. But if something goes wrong and an upgrade hoses your machine, you can just roll back to the previous snapshot of your root file system and nothing happens. This is a feature I like a lot. We also have boot environments, which I could give an entire other talk about, but I don't have time for, so you should go and look on papers.freebsd.org and find Alan's talk on boot environments, which will change your life. But that all aside, let's play a little guessing game. FreeBSD is a friendly, user-friendly Unix-like operating system. Imagine you wanted to create a Z pool of a single disk. Which commands do you think I should type? Z-pool, yes? Yeah. I would like to create one. Yes, this is very difficult. Now it becomes difficult, yes. Disks? No, the thing needs to have a name, right? Let's give the thing a name. Let's call it tank, because tank. Oh, do I have one called tank? No, I don't. How do I list my Z-pools? Shocking. These people are so smart. I have no tank yet. Before I do any of this, I think I should go and buy a disk, right? So how do I buy a disk? I walk to the store and I buy a disk. I would like to buy a very big disk. I have gone to the store and I have gone and bought a really big disk. I'm going to, right, zpool create, we said. Zpool create, what did we want to call it? We want to call it tank. How do I create this zpool tank consisting of one disk called disk 0? Any guesses? Oh, I lied. I need to actually go to the shop. I need to plug my disk in. Oops, and I need to learn how to type. Disk 0. There we go. I've gone to the shop, I've bought a disk, and I've plugged the disk in. Zpool create tank of disk 0. I'll just cheat here and call it, it's called MD0. So truncate will create a sparse file of 1 terabyte size, and mdconfig will create a memory device, which is backed by this one file. So to create a memory disk, you've now got those two commands, but that's not very interesting. We're not here to teach you about memory disks. I'm here to teach you about ZFS. Zpool create tank MD0 will create a storage pool. This took a very long time. How do I check whether it worked? Zpool list. Zpool, spell it right. List. Hooray, I now have 2 pools. I have my 1 terabyte tank. Did I actually spell it right? Yes, I did. I have my 1 terabyte tank, and I have my root file system, which is very good. Let's see, go back to my slides for a moment. Storage pools, how do they work? What are they for? Play from current slide. Here we go. So I've created my storage pool. I can just read this screen rather than breaking my neck. And ZFS can use disks directly. So you notice that at no stage did I create a partition table on this disk. I didn't do anything with gparts. I didn't do anything with fdisk, or didn't do any disk labeling. ZFS just uses your disk directly. Here is a disk, use it. I faked it by using a memory disk, but it could just be a real SCSI disk or SATA disk or SAS disk or what have you. MCA disks, anyone remember those? Any old disk, ZFS will just use it. There's no partitioning going on. ZFS is also going to automatically create a file system with the same name. So if you call the pool tank, ZFS is going to create a file system called tank on that pool, and it's going to mount it for you. So those are 3 steps which you don't even have to think about. Your storage is immediately available. If I go back to my Xterm here, I can type mount eventually. Hello. I can type mount, and we see that ZFS has mounted /tank for me automatically. So it's gone and created the /tank directory. It's mounted my file system there. I can touch hello on hello. And hello now exists. This is wonderful. I can also delete it because that's so much more fun. Tank, oops. Hello. I can create and remove files on this fancy new file system. Hooray. My laptop thinks that left is right, so I get confused. Right, your storage is immediately available. Also, you do not need to edit at ZFS tab. ZFS will remember where your file systems are mounted for you. And you just never need to touch this ZFS tab file ever again in your life. ZFS has a concept, oops, I'm using the wrong terminal. If I use this one, there we go. Ooh, they're nicely overlaid. ZFS has a concept of properties which you can set on your file systems. We'll come to that in a bit. If you move your file system mount points to another place in the file system, ZFS will remember this for you, and ZFS will mount your file system where you last mounted it. I think this is useful. Let's go back to the slides. So no needs to edit. Oh, woo, okay. Now my laptop is very confused. I should not have done that. Sorry, faffing around. Here we go. So ZFS makes your storage immediately available, and your ZFS tab file, you just don't need to think about that one. Right, displaying pool status, you can type zpool list, as we said. That works really well. You can also type zpool status, which is going to show you, actually stop looking at my slides, just do it in the terminal. So if you do zpool status tank, it tells you a whole bunch of things. It tells you that the state of the pool is online and it has 1 disk in it. If you have pools with multiple disks in it, the number of disks will grow. It'll also tell you about errors. So read errors, write errors, and checksum errors. The checksum category is the interesting thing about ZFS. Every file system tracks read and write errors. The checksum is something ZFS does for you. In the background, ZFS is doing all these checksums of your files and creating and maintaining its Merkle tree. If any file system or any file block starts getting corrupt, ZFS will start incrementing the checksum counter there. We'll see that later. ZFS also has a, oops, hello. Focus. Focus, he tells himself. There we go. ZFS can also tell you I/O statistics. So you can type ZFS I/O stats, and it'll tell you how busy your disks are. It can also tell you which of your disks are currently being written to and read from, and what bandwidth they're using. I'll just whiz through this because we don't have an awful lot of time. You can specify the interval, and it'll keep running indefinitely and just update every couple of minutes. So if you're suspecting that your disk is slow, you can just type ZFS zpool I/O stat, and it will tell you what the I/O going through your disks currently looks like. This is great fun. So we've now created storage pools. We've listed them. How do you think we get rid of them again? This is where we play the guessing game again. I don't want this tank anymore. How do I get rid of it? No, that's too nice. Destroy, destroy, zpool, destroy, tank. How long do you think this should take?
An hour.
It's gone. Yes. Destroy is instant. ZFS does not feel that you should waste any time destroying disks. This is a constant time operation. It is not in any way related to the size of your pool. So if you type ZFS destroy, or zpool destroy rather, on a pool containing, your life history, it will take exactly as long as this file system what I just created for this presentation. There are no seatbelts. ZFS is a file system for adults. So just bear this in mind. ZFS has lots of really nice features and lots of really nice snapshots, but if you shoot yourself in the foot, your foot is coming off whether you like it or not. Yes, so constant time operation, zpool create is also, it's a little bit slower and is in fact related to the size of your pool, but it's not terribly slow. So ZFS is a fast file system, and a lot of the really simple things in ZFS are constant time operations. The simple things are fast, and the not so simple things are reasonably high performance. Let me go back to the slides for a moment. Right, so destroying. Yes, all data on a destroyed pool is irretrievably lost. Of course, you could go and pay a data forensics person fantastic sums of money to go and restore your file system from there, but who wants to do that? Keep backups. Destruction is fast. So far we've just seen a disk or a pool rather, with exactly one disk. That's very nice, but it doesn't provide you with any redundancy. It's just one disk, and it doesn't balance the load across multiple disks because you only have one disk. So ZFS can also work on stripes or concatenated volumes if you like, and ZFS will stripe the data across multiple disks. So out I go to the shop again, and I go out and buy some more disks, and they're all the same size. Actually, let's make this interesting. Let's mix in some 4 terabyte disks. Do people sell 4 terabyte disks these days? I don't know. Let's buy a 4 point. Let's buy a 3.14159 terabyte disks, just because, just because we like this sort of thing. That's a bug. Please file a bug. All right, I cannot, yes, bug report, Bugzilla, cannot create disks of pi size. Right, great. Imagine, joking aside, imagine I wanted a pool called tank again, zpool create tank, we all got that. Imagine I wanted to have a pool of 1, 2, 3, 4 disks. What would I type here? I would just type the 4 disks, right? Well, actually, I'd plug the disks in first. What did I call them? 1, 2. If I were smart, I would just do a for loop, but I'm not very smart. Monkey of a little brain and all that. So we just zpool create, not destroy, create. There we go. MD1, MD2, and MD3. Oh no, it is part of an active pool tank. Oh, all right then. Let's just unplug this disk first. Oh, did I create tank? Online debugging. Oh, so I did. There we go. Destroy tank. There we go. You're gone. Now that'll work. Haha. Hooray. Zpool status. Spell it right. Really spell it right. There we go. I now have a pool with 4 disks, but these are just 4 disks, and ZFS is going to stripe my data across them. That's all very nice, but if any of these disks fails, in any way my whole array is toast. That's not cool. So let's get rid of this again before we accidentally use it for anything. How do we get rid of it? We just destroy it, right? Yep. Imagine I would like to have a little bit of redundancy in my life. What do you think I should do? This is the guessing game. FreeBSD is user-friendly. What do you think I would do if I wanted mirrors rather than stripes? Yes, very good. Where should I put the word mirror? There we go. See, this is not very difficult. You've done this course before, haven't you? The point of the guessing game is just to show you that ZFS is actually really easy. Oh no, I only have 15 minutes left and I haven't gotten anywhere. ZFS is going to complain if your disks are different sizes, and it's going to tell you exactly what to do if you want to override that. So I think that's enough about Z-pools. Let's go back to the slides and just go through them, because 45 minutes is really not very much time. So stripes are no redundancy, just your I/O bandwidth improves a bit, and you have slightly higher capacity. Mirrors, RAID 1, you just put the word mirror before the providers, ZFS calls them providers, that will be providing 1/2 of a mirror each. You can create mirrors of 4 devices, 5 devices, 8 devices, and ZFS will just write to each of those. Yes, you can have 5 identical copies of your data if you have more money than sense. But yes, you can do that. So the mirrored pools provide redundancy, but at the cost of a disk every time. So 5 disks, you get 5 copies of your data, but 5 copies of the receipts for the disk as well. Much more interesting are RAID Z groups, which are a little bit like RAID 5 or RAID 6, which provide parity. So RAID Z1 is roughly the same as RAID 5, where you have 1 parity disk. So you can lose 1 disk in your array, and you'll be fine. If you lose 2 disks, you're toast. RAID Z2, if you lose 2 disks, you're toast. So if you lose more than 2 disks, rather, you're toast. Lose 1 disk, everything is fine. Lose 2 disks, everything is still fine. Lose 3 disks, everything is terrible. RAID Z3 is the same thing again. You can have 1 parity disk. I think I have the formula here somewhere. A RAID Z group with n disks of 6, size X with P parity can hold approximately n minus P, blah, and can withstand P disks failing before integrity is compromised. I'm going to skip ahead to integrity at some point. All of this is not very interesting. Oh yes, increasing pool capacity. Basically, you just keep adding disks. And ZFS will be happy with that. You can turn a single disk pool into a mirror. That's very nice. I encourage everyone to just download these slides and play with this on your laptop. It is really easy and it is great fun. I'm just going to go to the PowerPoint has a slides index somewhere where I can go to something exciting. Right, so I've talked about pools enough. Let's talk about datasets. Datasets are what ZFS calls file systems, and a dataset is mounted automatically by default. So when you create your storage pool, you do zpool create tank. ZFS will create a file system called tank and mount it for you. If you want another file system, you just type ZFS create. So let's just do that. I think I have my pool. Do I? I do not. Let's just create my pool. Oops, there we go. I now have my pool. How would I create a file system? Any guesses? Zpool create creates a pool. How would I create a ZFS? Not everyone at once. ZFS create, yes. ZFS create, and then I want my file system on the tank pool, and let's call it users just for fun. And ZFS, this constant time. Where do you think this has been mounted? Tank users? Well, let's check that. It has indeed been put on tank users. Great fun. What if I wanted this to be read-only? Any guesses? You're allowed to guess. FreeBSD is nice. Type RO? No. ZFS sets. There we go. Let's it's probably an option, so it's probably called read-only. Read-only tank users. Oh no, that's not it. Read-only equals true, maybe? No? Yes. Or it's yes, or I think the -o needs to go. Read-only must be on or off. See, ZFS is friendly. It tells me these things. There we go. On. What do I need to do to make the file system mounted read-only? Exactly nothing, right? So if you set a ZFS setting, the file system will automatically be remounted with that setting. If I don't want the access time option, if I don't want my file system to be written to every time I look at a file, I would set A time off, which is the first thing you do on any file system, on any Unix machine, A time off tank users, and if we look at mount again, there we go. A time has been turned off. Hooray! This is easy. Let's go back to my slides for a moment. I have no idea what time it is or how much time I have left, so I'll just keep talking until someone tells me to stop. 10 minutes, oh no! So properties, we talked about read-only, we talked about A-time. The nice thing about properties on ZFS is ZFS inherits them from its parents. So if you have a whole tree of things, you want things to be read-only, just set the parents to read-only, and everything underneath there is going to be read-only as well. You can, the source of where it gets it from is in the outputs. So if it's inherited, ZFS will tell you this came from a parent. If it's a local property, ZFS will tell you these things. ZFS is going to mount things with the properties it keeps. That's all very nice. Read-only we've talked about. Exec is a useful property. If you don't want to ever execute code on this file system, say, you're not expecting anyone to run code on this file system, just set it as Noexec. This is a fun one. User-defined properties. I like this. You can set properties in your own namespace on file systems. You can use this for, say, backup features. Your backup tool can write under your own namespace when the last backup was created, and then your monitoring system can complain if that timestamp is too far in the past. You can also keep track of, who the storage needs to be billed to, or where you bought the storage from, and you can just track that in your file system. Whether your file system metadata is the best place to store these things, I would argue, put them in your accounting system instead. But ZFS supports quotas. Very simple. ZFS set quota will give you an upper limit on the number of blocks or number of bytes a user can store. That's easy enough. Play with that in your own time. Reservations are a special kind of quota. ZFS can ensure that there is always enough space available for some user or other. So other file systems do this for root. The root file system or the root user will always have 10% of your volume available. ZFS makes this a bit more generic. ZFS can say, right, I always want to have 500 megabytes available for user Bob, regardless of what anyone else is doing on this file system. That's a useful feature sometimes. Certainly saved me sometimes. ZFS has built-in compression. And again, properties are inherited. So ZFS, you set the compression on your top volume, and every volume underneath does that. The FreeBSD installer by default now sets LZ4 compression on your root file system for you. Compression doesn't only save you space, it also saves you time, because the compressed blocks are transferred from the disk to memory, compressed and then uncompressed, so you have a lot less I/O going on. So your slow disk, this is immensely useful on slow cloud providers. If you run them on UFS, I/O on cloud providers is hideously slow. So if you use ZFS with compression, suddenly your I/O speeds go up because there's less I/O. It goes faster. How do you set compression? You just ZFS set compression on, and suddenly it's compressed. For the FreeBSD ports tree, I think with LZ4, I don't think I do the example, but you can win about a third or so, depending on how much data you have. Yesterday or 2 days ago, I was backing up a NUC for a project I'm doing, and it was a file system of 400 gigabytes. It went down to 27 gigabytes, mostly because most of the blocks were zeros, but it just went down to nothing. So that was good. ZFS has snapshots, Copyonwrite snapshots. I really don't have a lot of time. A snapshot is a read-only copy of a data set or a volume. ZFS volumes just allow you to run other file systems on top of ZFS should you want to, but you can snapshot them like a ZFS disk. So snapshots occupy no space until the original data starts to diverge. So a snapshot is free until you start writing to the original file system. And they are hilariously fast, and you get used to them really quickly, to the point that my home directory has been on ZFS for 10 years. I delete files with abandon, and then suddenly I find myself on some other file system. I delete files with abandon, and I discover that I can't get them back. So ZFS again, it will not save you from using backups, but it'll save you from restoring backups too often. How do you create and list a snapshot? ZFS creates, ZFS lists. Apparently I have 5 minutes left, so I should speed up even further. I got about halfway through the slide deck, I should have you know. I'm not going to get to the end of the files. I'll just fast forward to something fun. ZFS has something called self-healing data, which I like to show off in real time, but with 5 minutes left, I can't do it. On a traditional mirrored file system, when you have a corrupt block on a disk, it'll go through the mirror, and the mirror will see the bad block, and the mirror has no idea that the bad block is there. So it passes the bad block up to the file system. The file system, if it's a bad block in a metadata block, the file system will panic, which is good news. That means nothing bad has happened. But the file system can't tell that it's a bad block, so it gives the bad block to the application. The application sees the bad block. This is terrible. Imagine you're an insurance provider and one bit has flipped. Someone goes from being, someone goes from being 30 years old to being 60 years old. Or that's not a one-bit flip. Do the maths in your head. One bit flips and someone doubles in age and suddenly, or halves in age and suddenly stops receiving pension benefits. Right? So this is terrible. ZFS, on the other hand, has self-healing data. So the ZFS sees the bad block, and it immediately goes and checks on the other disk. It gives the block from the other disk to the application, the good block, and it goes and fixes the bad block on the original disk. And it tells you, hey, one of your disks is starting to fail. Maybe you should do something about it. Does that make sense? This is great fun. So I do this as a demo. I can probably fit it in 5 minutes. Right, like ambition. I can't do it because extracting reports tree will take longer. Ask me during your break. So we'll be very sad if all this data gets lost. So we store some important data. Everything is fine. We've got hundreds or how much? We've got several gigabytes of data stored here, and then we go and destroy some data by writing dev random to one of the block devices. This is great fun. I destroy one of the disks, the ZFS goes, one of the more devices has experienced an unrecoverable error. Oh no. Applications are unaffected. This is good news. So ZFS tells you that, hey, one of your disks has started to fail, and this is not a problem for you now. Your application is unaffected. I have detected the problem, and ZFS is now going around and fixing the file system for me. And with no user interaction at all, your file systems may be a little bit slower, but things just move. Everything is okay, everything is fine, and after about a minute, ZFS will say, I have repaired 196 megabytes in 0 hours and 0 minutes. In the real world, of course, this is never going to be 0 hours and 0 minutes, but for this demo, that's all it took. Just for fun, it actually took me a long time to generate this problem. I went and corrupted 2 disks. This is unrecoverable. ZFS will tell you that, hey, applications may be affected and you'll have to go and restore your backups. Oh no, terrible, terrible things. But ZFS is really, really fun. If you add this -v to the output, it will tell you exactly which files have errors in them. Ha-ha, aha, aha. And if I notice that, oh, well, this FreeBSD disk1 iso.xz, I could go and find my backup tapes, or I could just go and download them from freebsd.org again. So this is one of the fun features of ZFS, is if things go terribly wrong, ZFS is still happy to tell you that, exactly what went wrong. And I'm out of time, unfortunately, so I ended this on a positive note. This is my favorite slide in the whole presentation. All right. If you would like the other half of this slides, they are all on papers.freebsd.org. If you would like FreeBSD, it is on freebsd.org as well. Go.